We all use tools like ChatGPT, right? And you've probably wondered, what's actually going on inside that black box? Sometimes it really can feel like magic. But today, we're going to pull back the curtain and unpack how a large language model is actually built, right from the ground up.
So yeah, let's move past this idea of digital wizardry and get into the real nuts and bolts. How does a machine learn to understand and generate human language, one step at a time? Okay, let's dive in.
You know, building a model like this really happens in 3 core stages. Sebastian Roschka lays this out perfectly in his book, Build a Large Language Model from Scratch. First, you have to get all your data ready and design the architecture. Second, you do what's called pre-training to create that foundational model. And third, you fine-tune it, which is kind of like specializing it for a specific job, like being a helpful assistant. We're going to focus on those first 2 stages because that's where we'll find the fundamental blueprint.
So, the most crucial point is, it all starts with the raw ingredient, text. And I don't mean just a little bit of it. We are talking about a massive, super diverse pile of text from all over the internet, from books, and from high-quality sources like Wikipedia. This is the diet the model is fed to learn about, well, pretty much everything.
Just how massive are we talking? Well, the GPT-3 model, that was the precursor to the original ChatGPT. It was trained on a selected subset of 300 billion tokens. Now, a token is roughly a word or sometimes just a piece of a word. That is just an astronomical amount of information.
And this chart gives us a great look at what that data is made of. The vast majority, look at that, over 80% comes from just crawling the web. The other slices are from book collections and Wikipedia. So in essence, the model learns the patterns of human language just by reading a huge portion of the public internet. Okay, this brings us to the first huge transformation we have to make. A computer can't process the sentence, "Your journey starts now," just like that. It doesn't see words. It only understands numbers. So all of this text has to be converted into a format the machine can actually work with.
The very first step is breaking the sentence down into its component parts, or what we call tokens. This process, as you can see right here, is called tokenization. We're just splitting the raw text into a nice, clean list of individual units that the model can handle.
This tokenization process lets the model create its own vocabulary of all the unique pieces it knows. But these tokens, they're still just labels at this point. The next, and you could argue most important step, is to give them real mathematical meaning.
And this is done through a process called word embedding. Essentially, every single token in the vocabulary gets assigned a unique list of numbers, a vector. And what's so amazing is that words with similar meanings, like king and queen or cat and dog, they end up as neighbors on this giant mathematical map. All of a sudden, the computer has a numerical way to understand the relationships between words. But language isn't just about individual words, right? It's all about context. The meaning of a word changes based on the words around it. So how does the model know that in the sentence, "the cat sat on the mat," the word "sat" is most strongly related to cat and mat?
This is the key challenge that older language models really struggled with, especially in long, complex sentences. The solution to this problem is the real secret sauce behind modern LLMs, and it's exactly what makes them so powerful. It's called the self-attention mechanism. Now, the concept here is what's really interesting. You can think of it like the model is reading a sentence, but with a magical highlighter. For every single word it looks at, it instantly highlights which other words in the sentence are most important for understanding its meaning in that specific context. This powerful attention mechanism is the heart of what's called the transformer architecture. Now, the original transformer had 2 parts, an encoder to understand the input and a decoder to generate the output, which is great for tasks like translation. But models like GPT simplify this. They use only the decoder, which is the generator part, and that makes them incredibly good at creating text.
So how is this powerful generator actually trained? Well, it's trained on a surprisingly simple task. Next word prediction. That's it. The model is given a chunk of text, and its only job is to guess the next word. It does this billions and billions of times, and by doing so, it builds this incredibly complex and nuanced understanding of language, grammar, and even how to reason.
And this simple training task leads to something pretty extraordinary. The model starts developing abilities it was never explicitly taught. It wasn't trained to be a translator or a summarizer, but because it learned the deep patterns of language, it can just do those things. These are called emergent behaviors. So we've unpacked the magic box, and it turns out it's not magic at all.
It's a logical process. You turn massive amounts of text into numbers, you use a clever mechanism called attention to understand context, and then you train the model on a very simple goal at an incredible scale. It's from this powerful foundation that models are then fine-tuned to become the specialized tools we use every day. The result is a system with abilities that can surprise even its own creators. This leaves us with a final fascinating thought. What will emerge next?